Hey everyone, this presentation is a summary of a journal paper we submitted last year concerning the development of a control module that would fit into an overall autonomous operation framework for advanced reactors. To start off, we would like to introduce and provide a motivation for the overall autonomous framework itself. And for that, I'd like to introduce my colleague, Roberto.
Thank you, Akshay. So yes, before getting into the technical detail, we would like to provide a little bit of background about the reasons why we want to pursue autonomous operation. So currently operated units are struggling to stay competitive in US deregulated markets. And the US Department of Energy identified the reduction of O&M costs as one of the most promising solutions to improve the profitability of these units. From an exhaustive literature review that we performed, we realized that the most effective way to reduce O&M cost consists in optimizing the maintenance schedule, in making the maintenance intervention less time consuming, in reducing the number of on-site technicians. So basically the lessons we learned is that we need to push for enhancing monitoring and diagnostics capabilities. Next slide, please. But at the same time, that's not enough, because monitoring and diagnostics capabilities are going to provide you information about the here and now, and this information gotta be used to make more optimal, if we can, decisions about the operation of the unit, and then we need to enforce this decision and make them real, through control action. So long story short, we need to integrate all these aspects, the monitoring tasks, the decision-making tasks, and the control tasks into a single integrated framework to achieve autonomous operation. Next, please. So in this slide, you can see a graphical representation of the control system architecture that we are proposing. As you can see, there are three modules labeled by control, diagnostics, and decision-making. There is a bidirectional data flow between these three modules. The one thing that you can notice is that we are leveraging AI/ML algorithms to fulfill the most error-prone repetitive tasks that are currently performed by human operators. Okay, and at the same time, we are preserving the structure that is approved by the US NRC. That is to say, the normal operation of the unit and the safety scenarios are two separated realms. And at the same time, the plant control system gotta stay separated from the plant protection system, and so on and so forth. So there are three modules in this work. We're going to focus our attention on the control module. Thank you, Akshay.
Thanks, Roberto, for the summary. So I'd like to highlight two key features of the control module at a very high level. So the first feature is that we retain the existing control logic that is used in conventional power plants, which is we have PID controllers at the lower level, and they're used to control very specific states using the major actuators in the plant. But then the second new feature that we have added is a supervisory control layer consisting of the reference governor. The reference governor is a control scheme that allows us to impose constraints on states that are not directly controlled. And the way it does this is by using a surrogate module to predict the propagation of states, and then suggesting when reference set points at the lower level may not be changed. So on the next slide, we have an example showing this. This slide has an animation of the results that were in the journal paper. So first I'll describe the layout of the slide itself. And on the left-hand side, we have a simplified schematic of the power plant that's modeled. It's a 320 megawatt pebble bed FHR, and there are four major components: the core, the intermediate heat exchanger, and the primary and secondary pumps. So on the bottom of the slide, we have the three major PID controllers. The first is used to control the core power using the reactivity insertion. And then we have the primary and secondary pumps, which are in regulation mode. So we manipulate the mass flow rates such that the core outlet and core inlet temperature are kept as close to constant as possible during power transients. So on the top of this panel, you can see the supervisory control layer's output. So here the reference governor is providing bounds by which the power can be manipulated. So in the beginning, we have a large admissible region and an inadmissible region at the bottom. What this means is that if the power is set across this boundary, we would violate a constraint. So specifically, we're applying a constraint on the secondary side of the heat exchanger, shown by this purple arrow here. So I'll let the animation start to play out. In the beginning, we're in the admissible region, and we're able to follow the requested decrease in power of the unit. But what you notice is that the admissible region is changing its shape depending on the state of the system itself. So at some point, an intersection between the admissible and inadmissible region is reached, and the first intervention occurs. What's interesting about this point is that the constraint has not yet been violated. So what this means is that the surrogate model we're using is predicting that there's a significant thermal lag, and maintaining the power at the current level would satisfy this constraint that we have imposed. So this is shown here where the blue line is overlapping the value that we've imposed for the constraint. And then at the bottom, you can see that the regulators are doing their job by keeping the core outlet and core inlet temperature as close to constant as possible. So the final feature we'd like to highlight is the capability of the reference governor to accept and update in the constraint value itself. So here we have relaxed the constraint a little bit, and the reference governor is able to take advantage of this additional admissible region that's available to meet the reduction in power. So Roberto, an important question for our audience to understand is, why is this capability important in the overall context of the autonomous operation framework?
Yes, because the answer is that, as we said at the beginning, the most effective way to accomplish savings on the O&M cost consists in improving the monitoring and diagnostics capabilities. But all these additional information content, we're going to make a good use of that. So to close the loop, we need a suitable supervisory control layer that can make a good use of this information, and they can basically close the loop between all these modules. Thank you.